Today we are going to talk about one of the critical tools that you'll kind of come across when you're doing statistical analysis. And one of the ways we could so far we've been giving bounds, like our population mean is going to fall between x bar plus or minus z confidence interval over 2 sx over square root of n. We've been dealing with bounds, but we haven't really kind of asked the question of, well, does a population mean, does a sample come from a population mean of this value, or does the sample come from a population mean greater than this value, or does a sample population come from a population with a mean less than this value? So if we want to test these hypotheses, we are going to use basically this hypothesis testing protocol and use statistical analysis to kind of see make certain decisions regarding a measure n. So the procedure is as follows. So we need to first define a null hypothesis. So we're going to set our population mean to a certain value, mu sub naught, a constant, specific value. Then we're going to define an alternative hypothesis. So let me go over here. Excuse me, skipped a page. So we're going to define an alternative hypothesis, H sub A. And that is going to be one of three tests. So it's either going to be a two-tailed test, a left-tailed test, or a right-tailed test. So we're either going to say our population mean, our alternative population is, it doesn't come from this sample, or that population mean. So the alternative hypothesis is that that sample does not come from the population mean specified in our null hypothesis. Or we'll say that that sample comes from a population mean less than that defined in the null hypothesis, i.e. that's a left-tailed test, because you'll see it's going to fall on the left side of our distribution. And then we also have a right-tailed test. So our sample comes from a population mean greater than that described in our null hypothesis. So a little bit kind of complicated, but again, it's going to be simple once we do some example problems. So this is our procedure for the hypothesis testing. Define the null hypothesis. Define the alternative hypothesis. Define your confidence interval. Calculate t experimental or your z experimental value. Determine the proper value of t alpha or t alpha over 2. Use the degree of freedom. If t experimental falls in the H naught region, we reject H naught, accept the alternative hypothesis. Does not fall in the region, we conclude we don't have enough sufficient data to reject H naught at the level specified. So that was a lot of information provided very, very quickly. I think the best way that you can kind of look at hypothesis testing is by doing an example. So let's look back at the data that we just looked at. So for phase change materials, PCMs. So the question is, does the previous data that the sample that we gathered, where we had our number of samples was 18, we had that our X bar was equal to, let's go back. Actually, let's look at our Mathematica notebook. We know our X bar was 2.054 milligrams. 2.04. We know our S of X was equal to, let's go back to Mathematica, 0.66, basically. Come on. So does this sample come from a population whose true mean weight is greater than 2 milligrams, assuming a confidence level of 99%? So let's follow this procedure. So from this problem statement 1, what is our null hypothesis? So the null hypothesis is, or the alternative hypothesis is given in here. But whenever you read this data set, it's asking, does the sample come from a population whose true weight is greater than 2 milligrams? So our null hypothesis, our H naught, is that mu equals, basically our mu equals mu naught, which is, in this case, our mu naught is 2 milligrams. Our alternative hypothesis stated here, what we're trying to test is, we're saying, or we're kind of trying to predict, does it come from we're saying no, it comes from, or does it come from a population whose true mean is greater than mu naught, which is it greater than 2 milligrams? So is it greater than mu naught? That's the question. 3, what's our confidence interval here? Well, confidence interval of 95%, of 99%, 99%. So we know that our alpha is equal to 0.1. And now we need to calculate t experimental. So your t experimental is just X bar minus mu naught. Again, this just comes from your t value, calculating t, Sx over square root of n, where mu naught, remember, is equal to 2 milligrams. So if you calculate that out, we find that our t experimental is 0.035. Again, you can check that in your Mathematica notebook. we need, now this is a key question, T alpha or T alpha over 2. So let's look, and I would have this, I'd have this page right next to you during your exam. So this is a really kind of cool tool to see what T alpha over 2, kind of like the theoretical value that you need. So when you're doing hypothesis testing, I would have this next to you. So we are doing a right-tailed test. So we're doing the green one right here. So I'm looking at my distribution. So the first thing you kind of plot out, show here, is this T alpha value. So why is this T alpha not T alpha over 2? For the two-tailed test, I have this T alpha over 2, and the right-tailed, left-tailed, I only have T alpha. Well, because we're not concerned about whether it falls within these two bounds. We're just saying, is it greater than a certain value? So the first thing you have to do, we want to kind of show here, is that this dash value is that T alpha over 2, or like that theoretical, that value you find in your T table. So what is my T alpha value? Well, I know my alpha from that previous problem is 0.01, because we're looking at a confidence interval of 99%, so equals 0.99. So we know that it has to be, this has to be 1 minus alpha. Excuse me. So my alpha is 0.01. My nu, I know that my number of samples is 18, so 17. Let's look at our T table right here. 0.01, 17, 2.576. So my T alpha is going to be 2.576, as we see here. So if I look back at my presentation, so this value is 2.576 right here. So this is my reject region. Reject H naught. Do not reject. Do not reject H naught. So where does my T experimental? So this is again my T alpha nu. Where is my T experimental value? Well, it's over here, right? My T experimental value was only 0.35. So this is 0.35. So our T experimental value is equal to T experimental. This falls in the do not reject region. So looking back at our hypothesis interval, if T experimental falls in the do not reject region, we conclude we do not have sufficient data to reject H naught at the level of confidence specified. This is a kind of very, this is where statisticians will get really mad. We do not, if it falls in the H naught region, we reject H naught and we accept the alternative hypothesis. But if it falls in the do not reject H naught, we do not have sufficient data to reject H naught. So we're not claiming, if it falls in the do not reject H naught region, we are not saying that we accept H naught. If it falls in the reject H naught, then we are accepting the alternative hypothesis. But this is just, again, we don't have enough data to basically to reject H naught at the level of confidence specified. So that's the statement that you want to write. Honestly, I'd be fine in your problem sets and exams if you just write reject H naught, do not reject H naught. I'm definitely fine with that in our analysis and in this class. Again, we're engineers, we're mechanical engineers, we're not statisticians. I'd be fine with that. But again, if you're really into that, and if you've taken a statistics course and you just can't bring yourself to kind of write a statement, and you want to kind of be very, very precise, more power to you. So that's our first confidence interval exercise. So we'll do a couple more examples, and we'll do a t-test comparison, and then we'll be done with lecture 3. All right. Great job. I will talk to you all next time. And yeah, be safe. And let me know if you have any questions. Bye.